Hello and welcome to Week 8, Lecture 3 of CO 442642 Graph Theory. Today we'll be discussing Hadwiger's conjecture. So what is Hadwiger's conjecture? Well, in 1943, Hadwiger conjectured that for every t at least 1, every graph with no kt minor is t minus 1 colorable. So what is this conjecture about or saying? Well, it relates two fundamental concepts which we've already studied in this class in graph theory, namely minors and coloring. So it's really asking a question in a conjecture of a more general question. How are minor and coloring related? Right? So again, remember minor in the sense of models as finding many pairwise, disjoint touching, adjacent subgraphs. And remember, coloring is decomposing into independent sets. So what this conjecture is really asking is there some relation between that if we couldn't find many disjoint adjacent subgraphs, then perhaps we may actually be able to partition the graph into many independent sets. So there's no reason a priori that these concepts should be in any sense dual or related, but that is the nature of the conjecture. And not only that they are related by some function, but by kind of a very exact function. The no kt minor is t minus 1 colorable. This, which would be best possible, of course, because you could have kt minus 1, which is t minus 1 colorable with no kt minor. So today we'll be going through this, its weakenings, its generalizations, what's known about it, what bounds we can get, all the various history. And still we won't cover all the work on the subject. So let's go over what is known for the special cases, for the logt. So when k is 1, 0 colorable, that's easy. K2 minor is an independent set, 1 colorable, that's easy. K3 minors are 2 colorable, that's saying that forests are bipartite, so that's easy. The K4 case is a little harder, but Hadwiger in 1943 and Dirac independently in 1952 proved it for T at most 4, namely, importantly for the T being 4 case, so that no K4 minor is 3 colorable. However, if you remember from our discussion on the structure of graphs with no KT minor for small t, you'll remember that no K4 minor, those series parallel graphs, are made from the, at most, 2 sums of triangles and subgraphs thereof. So they always have a vertex of degree at most 2, they're 2 degenerate, and so they're 3 colorable. So that's really the proof for the t equal 4 case. What about the next case? Well, Wagner in 1937, 6 years before Hadwiger made his conjecture, showed that the t equal 5 case is equivalent to the 4-color theorem, which was proved by Oppel and Hawken in 1977. So why is that? Remember that graphs with no K5 minor contain the planar graphs, so it certainly implies the 4-color theorem, but that Wagner had showed that the planar graphs plus 3 sums of what we call V8. And so if you think about what that means, well, 3 sums will work for colorability, and then V8 turns out is actually 4 colorable, so you can indeed color as long as you know that planar graphs are 4 colorable. So that's how Wagner showed that they're equivalent by describing the structure of graphs with no K5 minor. And then, the 5 case was done by Oppel and Hawken in the 4-color theorem, the history we've already talked about for that one. And then the next case that was known as the t equals 6 case. The no K6 minor is 5 colorable. And this was shown by Robertson, Seymour, and Thomas in 1993 by showing that it's equivalent to the 4-color theorem and hence true. And that in some ways motivated, I think, also a reproof of the 4-color theorem. But why do we say equivalent? Well, actually the t equals 6 case still implies the 4-color theorem, because you could take planar graphs and add 1 apex vertex adjacent to everything. They won't contain K6 minors, but to show they're 5 colorable, you'd have to show that planar graphs are 4 colorable. So certainly you need the 4-color theorem, but they relied on it as a black box then and showed that it's equivalent. So really they give a 150 page handwritten proof that reduces the case to the 4-color theorem. So uses the 4-color theorem as a black box. So it's an impressive feat on its own then, Also want to focus and prize another very nice result. And that's it. It's open for every t at least 7. So no k7 minor seems very, very hard. And anything beyond that, just harder still, as you'll always need the 4-color theorem as a special case. You'll always have to use it as a black box. But then the structure of graphs with no kt minor gets harder. Okay, so that's what's known. For what t is it known? Instead, we could talk about general bounds then. So maybe this is the other direction to go. Instead of asking, can we prove it for given t, we can ask what, for general t, can we do? So what is the relation between no kt minor and colorability? And as alluded to in the last lecture, large average degree forces a large complete minor. So Kostachka and Thomason in the early 80s had shown that every graph with no kt minor is OT root log t degenerate, and hence O of t root log t colorable, right, by degeneracy. So we have this average degree bound, and that implies something about the colorability, and t root log t is not a terrible bound in that sense. So that was the state of the art, this t root log t bound. There have been some minor improvements over the years. So Thomason figured out the exact number in 2001. Wood improved with some, I think, additive factor in 2013. With Tom Kelly, we did a multiplicative factor, but really the t root log t had not been changed at all in the ensuing 35 years. Until 2019, when Noreen and Song broke this barrier. So they actually show that every graph with no kt minor is OT log t beta. They did it for beta about 0.34 or so, and I came in and worked on the project, and we improved this to any t log t to the beta for any beta greater than a quarter. So that's kind of where we were at, so making the first improvement on the general bound until just this year when I was able to show that for every beta greater than 0, every graph with no kt minor is OT log t beta colorable. More specifically, they are O of t log t to the 6th colorable. So we've managed to get rid of the square root log t and get it down to a poly log factor. So I think these results are nice, and I'll talk through a little bit about how their proofs go in this lecture. But you can, of course, look at the papers and all these papers on the archive and such for more details. But what's the nice part maybe about these last things is that now there is a difference. So it used to be that the best argument in general for general t was basically an average degree argument. It didn't really use anything about coloring specifically, other than that large average degree forces large complete minors. And we know, as I alluded to, that the Kostachka-Thomason proof is tight for random graphs. So, you can't improve just from average degree. So you're going to need some use of coloring to prove Hadwiger's. And that's what this was doing, was saying, oh, we can actually use some coloring techniques to make improvements. Okay, so that was that. Now I want to move on to some weakenings. I should also maybe say before I get there that Hadwiger's is very natural as a combination of minors and coloring, and you can view it in two ways: as either structural graph theory, answering a fundamental relation, as I suggested, between two very structural concepts, coloring and minors, or, as we'll talk about next week, it could actually be viewed as an extremal graph theory question, which is how it appears in D-Store. That, what is the maximum chromatic number of graphs with no kt minor, a certain extremal question. And you can also ask this about other things. So, for example, what's the relation between minors and independent sets? So what's kind of the maximum independent set of a graph with no kt minor? And this would then be a weakening of Hadwiger's, because if you believed Hadwiger's, you'd assume there would be a color class with at least v over t minus 1 vertices. There'd be some independent set. And Duché-Menil proved some weaker version of that you can get a independent set of size at least v of g over 2t minus 1. And this is from 1982. So a nice result in that sense. And we're going to go ahead and give you a proof of that. So again, a weakening. And I shouldn't have said that, so while Hadwiger's seems really hard, there's another conjecture, which is that the linear version of Hadwiger's is true. That maybe it could be true with 2t or 3t, or really be happy if you said 1,000,000 t, would seem to be very nice. And could we could we prove that? It would have, that kind of thing would avoid some of the problems of the hardness coming from the four-color theorem. And so that's maybe how you should view this Duché and Méniel as the linear independent set version of Hadwiger's. Okay, so now on to the proof. So how would we prove this? Well, we're going to do it by induction on T. So we should, of course, have had a base case. The base case would be, if T is 2, if you have no K2 minor, you're just an independent set, so then you'd be done without even the slack. But then, in general, for the general case, we'll do the following. We'll let A and B be disjoint subsets of V of G such that we have the following. We'll let A be an independent set. We'll have A be larger than B, and we'll ensure that G induced on A union B is connected. So kind of imagine you kind of have this subgraph which has a kind of a core, at least half the vertices lying in some independent set. Okay. And it doesn't have to be by part that, B could not be an independent set, just A. And then subject to all of that will maximize the size of A. So this is the object we'll find. Again, this should be reminiscent of some of the proofs from last time. You set up some object in a certain way and maximize it, and we'll see how to use it. So how do you do this? Well, if A is large, then we're just done. So we may assume that A is actually smaller than the target of, say, V of G over 2t minus 1. As otherwise we're done. And then there are cases. So then the cases go through that for every vertex of G prime, then if every vertex of what will define G prime to be G minus A union B has a neighbor in A union B, then G prime has no KT minus 1 minor. Right? So then you'd have no KT minus 1 minor, and then you just kind of, why is that? Do you see why that is? Because our A union B is connected, so we can contract it, and then if this case holds, we're adjacent to everything. So if you find a KT minus 1 minor in G prime, you'd have it KT minor in G. Then you just apply induction, you work out the numbers, and it turns out then that you indeed get, so that's a typo, there should be no 2 in the middle term, but you get alpha as at least V of G prime over 2t minus 2. You get kind of 1 minus 1 over t minus 1, not a 2 there, because A is, you're deleting A and B, but A is at most V of G over 2t minus 1, and B is at most A. And then you cross multiply and you get V of G over 2t minus 1, which is the desired case. Case 2, otherwise, says that there exists a U in V of G prime. So what does it mean? If not everybody's a neighbor, there'd have to be somebody that's far away. And here we're assuming that you're obviously connected, because we could just do this on different connected components. And then we have that D of U A union B would be 2. And then we let V, we pick a neighbor V of A and B and U. So we kind of take a path U, V to A union B. And then we have A prime be A union U, so U is non-adjacent to anything in A, so we can add it to the independent set. And then we set a B prime to be B union B, contradicting the maximality of EB. So that's a nice, quick proof to show you how that works. I'll move on and say, what more can you do besides independent sets? Well, Reed and Seymour and another breakthrough result from 1998 showed that for every T at least 2, every graph G with no KT minor has actually fractional chromatic number at most 2t minus 1. So we won't get into that. We haven't talked much about fractional coloring, but where you want to color with kind of fractional bits of color, and that it has a dual form from linear optimization of weighted independent sets. So this is a strict generalization of the Duché and Méniel, and says that, again, in some sense, Hadwiger's holds, at least in independent sets, or more generally for fractional coloring. All right, let's move on to other weakenings. So there's been a number of works in the recent decade on kind of proving Hadwiger's with somewhat weaker assumptions. So how might you do this? One way is to change the notion, instead of independent sets of fractional color, to change the color classes themselves. So we say a D-defective coloring of a graph G is an improper coloring. So I allow improper colors where each color class has maximum degree at most D. So kind of, could I partition into low degree subgraphs, not independent sets, just low degree. And this was a result of Edwards, Kang, Kim, and Seymour from 2015, that for every T, there is some D, such that G has no KT minor, then you have a D defective coloring with T minus 1 colors, the right number of colors. And so that would again be, we won't go through that, but is type, the number of colors. So I think that's a very nice result, and the proof is maybe only a page, so if we had more time, we would cover it, but maybe go read it yourself. But in spirit, that's another evidence that in spirit, Hadwiger's is true, if we relax the notion of the color class. I should mention that their defect is not really that bad. It's on the order of something like t squared log t, and that Vanden Heuvel and Wood in just 2018 improved it to another best possible defect of t minus 2 with the same t minus 1 colors. So very nice results there. And then another stronger version of this is, instead of going for the degree, you can do what's called clustered coloring. So a C clustered coloring of graph G is an improper coloring of G, where each color class has maximum component size in most C. Right? So of course, if you have maximum component size C, you'd have maximum degree, C minus 1. So clustered would imply defective, but not necessarily vice versa. So kind of allowing not only monochromatic degree, but asking stronger that instead that all of the monochromatic parts are clumped together into small components. And then it's natural to ask, can we say that for every T there's a C such that G has no KT minor? Then you can have a C defective coloring, but with some function of T colors. And ideally we'd like T minus 1 there. So what was known, this was worked on by many people over the years, so we'll just run through it. Kobayashi and Mohar in 07 had shown the first bound, and it was linear actually, 31t over 2. Wood, I improved this to 7t minus 3 over 2. Edwards et al., the same people from the last slide, 4t minus 4. Liu and Ohm, 2015 as well, 3t minus 3. Vanden Heuvel and Wood to 2t minus 2, and it's been announced by Dvorak and Noreen that you can get to t minus 1. So that would then prove the clustered version of Hadwiger's, but those get progressively, I think, a bit harder as a result, especially the last one there, maybe relying on graph minor structure theory a bit. So that's just to show you some weakenings, the independent sets, the defective coloring, the clustered coloring, that in some ways Hadwiger's is true. Now I wanted to focus back on, try to give you a sense maybe of the proofs from the latest ones. We didn't do the Kostachka-Thomason bound, but that's just degeneracy. But how much you break that, how much you do the quarter, how much you do the log-log. So let's talk about the quarter one first. For this, I can explain it in a few slides. So a corollary of the Duché and Menil result is that if G is a graph with no KT minor, and the number of vertices is something like T polylog T, then chi is at most T log T. Why? Because you could just pull out these large independent sets as colors. And so you could, you could reduce the size of the graph multiplicatively with about T colors. And so if you kind of keep doing that, you can get down, you can just kind of keep pulling out and always reducing by, say, a factor of 2 or so, or a factor of, E, something like that. And then how long does that take to color the whole graph? Well, you'll need kind of log T number of such steps. So at least to get it down to the range when then you could color with that number of colors. So there's that proof, so we won't go through that in more detail, but note that small graphs have better numbers than the T root log T, simply from this independent set version. Now it's still an annoying open question that we don't know how to improve this to actually that they should be satisfying Hadwiger's or even linear Hadwiger's, and it'd be very nice to do that. Now, to finish off the quarter proof, let me go through the idea. So let's say let f of t be this log t to the 6th, this additional term. This is where the density increment theorem from last time comes in. So a corollary of the density increment theorem is that if G is a graph and the density is at least k times this f of t, this kind of error term, then G contains no KT minor, and G contains no KT minor, then you have a small dense subgraph. That the number of vertices is the most T, ft log t, and the density is at least 2k. So why is that? You just run the density increment theorem with the big D being the Kostochka-Thomason bound of t root log t. And if you work it out, this is what you would get. Then if you invoke Motter's theorem, which we covered last class, if the density is at least 2k, we know it actually contains a k-connected subgraph. So you can improve this actually to find not only a small dense graph, but a small connected subgraph, highly connected subgraph. And that's really the key that we're going to use. We're going to use these small connected subgraphs to build our minor. Why do I say subgraphs plural? Well, you can actually repeatedly do this. So let's go through that. If G is a graph with no kt minor, and chi is, here's some value, it'll be like the kft you need for the above theorem, and then something like t log f of t, which is like log, 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 that's not bad, and 6t log r, then you actually can find r vertex disjoint k-connected subgraphs, h1 up to hr, that are all small. So why is that? Well, because, from the above corollary, you pull out a small dense subgraph, and then what happens? Well, those are easy to color by the Duché-Meniel corollary. So then if we could color the rest of the graph with few colors, we'd be done. So then the rest of it still must be dense. And if it's still dense, then we can pull out a second one, a third one, and in this way pull up to R. So think about that. But let's just take that as granted, that from Duché and Meniel and the density increment theorem and Motter's, you can pull out lots of these subgraphs. Then what do? Well, then here's how we build a minor, say when chi is on the order of t log t to the quarter times this kind of log log t to the sixth factor. So that first improvement theorem. How do we do it? Well, we'll let y be log t to the quarter, and we'll let x be t over y, which is t over log t to the quarter. Then by the Girard-Neronian theorem from last time, we can assume that you're actually xy squared, which is t log t to the quarter, ft connected, right? That only losing a linear factor, we can assume we're high chromatic number and highly connected. So why is that good? Well, now we also have by the density increment corollary that there are lots of these small subgraphs. So let me name them. Let's say there are y squared plus y over 2 plus 1 vertex disjoint, this omega xy squared connected subgraphs. So we lose the f of t factor by the density increment corollary. And let's give them names. There'll be h0 and hij, and it'll look like this picture. So what do I have? I have an h0, which will be a hub to kind of link up and build the parts of my model, my minor. And then I'm going to make pairs. I only need the upper triangular. I'm going to do h11, h12, h13, h22, h23, etc. And so I'm going to have all these little subgraphs. And then the idea is that, I have kind of, so I have kind of this y by y kind of triangular, upper triangular grid. And so I'll build my minor in y parts. So I'll kind of have y parts of x size each. And I just need each XX pair to go to one of these little subgraphs and then find a minor there. So how do I do that more precisely? In H0 we'll have vertices Si, which will be Sijk, and in Hij we'll have Tijs. And then because they're linked, we'll link up kind of, from the hub to kind of pairs to each small subgraph. So we do that, and now the idea is we can find large complete minors in each of these subgraphs, and then because a hub is also connected, we'll be able to link them all as we want in the hub and form a minor that way. So again, pause if you need and think through this argument, and you go read the papers, but I think that's very nice that you can really build the minor through the use of these small subgraphs. So use the small subgraphs to kind of do the little buildings and then link everything up. Right, and here again, note that we used the Buller-Bosch-Thomason theorem as to why the whole graph is xy squared linked, because it's highly connected. So we're also using that. And now we're almost done, right? Well, let me talk a little bit about how you build inside the subgraph. So what do we have? We have to build a K2X minor on those vertices, the Tij, inside of Hij. However, we have to do this while still preserving, we find these paths to help do the linking. We would like to build the minor and preserve the path. And that's where the weaving comes in, right? So then that's where the weaving will come in. So let me back up. That actually, now we use the Noreen Song-Woven theorem. So it turns out you have the right number that you can not only weave a complete minor on the Tij, you can do it disjoint to the linkage. Now that's a little bit of a lie, because you might complain, what if the blue paths go in and out of my small subgraphs, so the number of paths is much larger, these small subpaths is much larger, but I really only need to connect the very first part that enters to the very last part that goes out. I don't have to preserve the little wiggles in and out. So in that sense, once you realize that, then actually you have xy squared paths to preserve inside, and you do that. So each little subgraph, you weave a complete minor, and you do this one at a time, and maybe the paths get shorter in the overall, but you preserve them, and you do that, and you build all these small graphs. And then back in the hub, you just use the fact that it's also linked to just link up kind of all the S1s together, all the S2s together, etc., to build then complete minors. So hopefully that made some sense. So we use a lot of ingredients, the Generalizations, we use linkage, we use the woven theorem, we add that all together to build our minor. So now how do you get rid of the quarter though? So the quarter shows up because we kind of needed to be able to find minors inside the small subgraphs, and that was kind of costly. Well, here's the big idea for the log to the sixth bound. I call it chromatic separability. So we say a graph G is S-chromatic separable if there exist two vertex disjoint subgraphs H1 and H2 of G, where chi of Hi is at least chi of G minus S, and you're S-chromatic inseparable otherwise. So what is this saying? Could you find two kind of high chromatic subgraphs inside that only lose a little bit? This would be nice, like somehow the high chromaticness separates over two still pretty high. Now, if you think about it, a graph of chromatic number chi of G always have like two subgraphs of roughly chi of G over 2, but here we're thinking S is much, much smaller than chi, so we're just going to pay a little bit and be able to separate into two high chromatic subgraphs. But that might not always happen. So, for example, cliques are not that kind of chromatic separability, so they'd be on the inseparable part. But then we separate into two cases. So we'll either be always separable or we'll be inseparable. So we make kind of two lemmas. You're either, if your chi is at least S log t, and every subgraph of, say, at least half chromatic number, or kind of large chromatic number, is S chromatic separable, we'll be able to find a KT minor then. And alternately, in the inseparable case, if you're S chromatic inseparable, where S is like T log t, then we can do it if chi is at least T with this log t to the 6, this F in there as well. So what is that saying? It's saying, like, we have these two cases, and why do two cases naturally come up? Well, how do you build a minor, right? How do you build a minor? In the example of the quarter, we kind of used these small subgraphs, and then we built it all at once. We linked all at once, and we wove, but we kind of built it all on one global stage. And here the idea is there are better ways to build a minor. So one way to do this for the always separable case is to recursively build a minor, right? So what you do is you build kind of three K2 over T over 3 models, and you link them. So what's the idea is, I could find two, and actually if you repeat it again, 3 kind of high chromatic subgraphs, which by Generalizations would have high connectivity, and then I can link into them and recursively keep doing that. So I kind of build downward recursively until we can just find small minors on the leaves. So I won't get into that, and you can watch my talk on this, which goes through more of this detail. I'll read the paper. But one way is recursive. What's the other way? In the inseparable case, you sequentially build a minor. And so what you do is you successively build up a KT model, adding about root log t new vertices at a time. So how should you think of that? Well, remember the picture from the quarter case. Instead of building the entire upper triangular grid, you build it kind of just one new column at a time. Or if you want to think row equivalent, but kind of only do one slice at a time, and that's going to use up less connectivity to do it. Now that's harder, because how do you know you can continue on and keep building? So there's a lot of details there that I'm hiding, but I just think this is a very nice idea of like how do you really build, minors. So small subgraphs is nice, but also what really gets you to the log thing is recursive or sequential and dividing into cases. Okay, so then you could prove the main theorem we had, the log to the sixth, by saying that actually if your S is T log T, then you go through the cases. If you're always separable, we're done. So you would have to have an chromatic inseparable subgraph, and you apply the inseparable lemma, and then you're done. So you can pause and read that, but basically, yeah, divide into two cases like this, and it will work. So in my little time remaining, I just thought I would mention some generalizations of Hadwiger's that people have asked. Now, it's a little bit weird because why ask about generalizations, if we haven't yet proved Hadwiger's, but it goes to show, there's all these nice weakenings, but there's even maybe more. So Hadwiger's nicely straddles its weakenings to its generalizations. So one generalization is something called an odd minor. So we say a graph G contains H as an odd minor if you can get a subgraph isomorphic to H from some subgraph of G prime of G by contracting a set of edges forming a cut. So it's kind of, the oddness is you kind of think of every part of the model as being a bipartite graph, but you make sure the edges across only go between kind of monochromatic parts, from ones to ones everywhere. So I won't draw a picture of that, but it's a nice notion to find these kind of more structurally odd minors. And it was conjectured by Gerards and Seymour in the early 90s that the odd Hadwiger's holds, that no odd KT minor implies T minus 1 colorable. And Gielen, Gerards, Reed, Seymour, and Vetta in 08 had shown you get T root log T colorable. Now that should match the Kostochka-Thomason bound, but high average degree is not enough to force a large odd KT minor, unfortunately, because bipartite graphs have no odd K3 minor. But they were able to massage the arguments to use kind of other things as well, then to still retain the old bound from Kostochka and Thomason. And then Noreen and Song were able to get the quarter proof to work for odd minors, and then just this year I was able to get the log 6 proof to also work for odd minors, but that takes some more ideas. And the last generalization I want to talk about is again list coloring. It's natural, right, to ask if it could hold for list coloring, that no KT minor means your T minus 1 list color. But that you already know to be false in general, because as we talked about for list coloring planar graphs, Margit Voigt had shown that there exists a planar graph that's not 4 list colorable, right? So hence list Hadwiger's is false. Now, in spirit it's true because, Thomason you get the 5 list, so maybe you would think it's only off by +1 or something, but actually Barat, Jouret, and Wood extended Voigt's construction to construct graphs with no K3 T plus 2 minor, which are not 4 T list colorable, for every T at least 1. So it's not even off by like a +1. At best, you could get a 4/3 T ratio. But it still might be true that linear list Hadwiger's is. So it's quite interesting that there is something about Hadwiger's, just as like the 4-color theorem, it's something specific to coloring and not list coloring. But maybe the linear version also works for list coloring. And so what's known, well, the Kostochka and Thomason degeneracy bounds, if you remember our talks on list coloring, certainly imply that they're T root log T list colorable. And then with Sergei Noreen and myself, we adapted the quarter proof to work for list coloring, and then just this year, very recently, adapted the T log T to the 6th proof to work for list coloring as well. And so that's where we are on the state of things. So we went over Hadwiger's conjecture. We talked through its various weakenings and showed off this nice Duché-Menil proof, which should be kind of reminiscent of last time. But, we went through a lot of the nice weakenings, the defective, the clustered, where it really has been proven. And then these very recent proofs, which aren't even, in D-stool yet or anything, showing off how to get to T log T to the quarter. So we kind of went through that one, where we needed ideas like woven and linked, how to color small graphs, etc. And then the log to the 6th one, which I didn't, have a lot of time to go through, but I thought nice to show off the idea of recursive and sequential, and that seems very nice as ideas as well. So that's kind of the state of art of Hadwiger's conjecture, arguably one of the most famous and important problems in graph theory, and which has spurred a lot of work, I think people should remember over the years, how the Hadwigers and Kuratowski and these things have spurred a lot of work on minors, and then led maybe arguably to the graph minor theorem, but they've also spurred a lot of work on, Kostatka-Thomason, this kind of degeneracy extremal arguments, to Bolobosh, Thomason arguably, and some of these linked arguments coming from subdivisions and such. So it's led off into all this different work, to the weakenings, to the generalizations, as kind of a nexus that are coloring and minors related. So I thought this was a nice time to bring this in as a window, as we spend a lot of the class talking about colorings. So that's what this is about, but also about minors and the structural theory here, and Hadwiger's nicely relates the two. But also in a very sense, it's also an extremal graph theory question. What is the largest chromatic number of KT minor free graphs? And that's why D still includes it in his extremal graph theory chapter, which is where we'll be going next. We'll be venturing off into extremal graph theory of Taran's theorem, to Ramsey theory, to probabilistic methods, and so on, kind of turning the page from somehow more structural to more extremal and probabilistic results in graph theory. But I thought this was the nice in-between. So until next time, see you then.